discussing two presentations. They're both in the same realm. They're both in the realm of having more efficient inference engines for generative AI. One is Ming Ding. He's a researcher out of China, which is actually an interesting company, Zhipu AI, I think, something like that. It's kind of like an open AI clone in China. Researchers working on large language models, video generation models, things like that. So he gave a presentation. And then there is Atila Orhan. He gave a presentation too. He was talking about efficient machine learning models for edge devices. Let me start with Atila, actually, and then talk about Ming Ding. Atila used to work for Apple, so he's definitely sort of in that space of having efficient inference engines for edge devices. This is not even on podcast. It's May 10, 2024. This is Krimdelko. For the fund is down 1%. The market's flat for the year. We're down 19%. Market's up 9%. We're underperformed by 28%. Atila Orhan, he is the founder of a company called Argmax. They're a company that is commercializing an open source project which is helping with inference. So what do I mean with that? So imagine you have a large language model, let's say GPT, which has all the generative AI capabilities that we're familiar with. And you want to be able to use that model on an iPhone or on a car like a Tesla. The problem with that is that you have too much data, you need too much memory for all the weights to be stored and all the biases to be stored, basically all the parameters, right? We're talking about trillions of parameters that need to be stored and used when there's inference. So, I mean, the whole idea of doing inference is to use the pre-trained model or even a fine-tuned model for that matter and do something with it. And the question that Atila is trying to solve is, can we reduce that model? Can we compress that model to the point where we get similar results, but with much, much less weights and biases being stored in memory? That's the problem they're trying to solve. And here's just one example of how they're doing this, which I think is just interesting. So what they're doing is they take a model, and just for simplicity, let's say I have a model with 100 parameters. And I reduce that model to 10 parameters. So I take the model and I say, okay, look, I'm going to get rid of 90 parameters and just keep 10. And then I'm going to feed the one with 100 parameters some random noise and see what it generates out of that. So I give it, let's say, a certain prompt. I say, please, what is the name of the mouse at Disney? And the answer would be, it's Mickey Mouse. And then I take the model with 10 parameters and ask the same question and see if it says it's Mickey Mouse, then that tells me that, okay, for a question like that, my distilled model now still works pretty fine. So you can already see, like, part of the problem here is, of course, okay, how do I even test whether my model is still good enough or not? So this is kind of the work that they're doing. So it's more of a tinkering approach. Just as a side note, which I find interesting, is Atila is actually he has a master's in electrical engineering. So this is more of an engineering problem than maybe a theoretical comp sci problem, something like that, where you just keep trying, right? You look at the weights and the biases, and you just sort of reduce. You know, it reminds me of Rick Rubin and the way he produces music. You know, he has a nickname. He's a reducer, not a producer, and that just means that he takes a Chili Pepper song and he literally distills it into, okay, this is the essence of the song. Let's keep that and throw everything else away. So it's kind of like that. Like, you could also think of it like maybe borrow from quantum computing and think about it like this is like an eigensolver, where you just try to find the essence of the model, the absolute necessary weights and biases that are necessary to keep a certain amount of performance. And this is definitely an engineering problem also, in the sense that This is, you can distill a lot and maybe lose 10% of performance, but that's still good enough. For most use cases, particularly, let's say on an iPhone, if I just want to compare pictures and things along those lines, I mean, that I don't need all the billions or trillions of parameters. But if I want to do more interesting inference, then maybe I do. So those are the kinds of questions that Atila is solving. And I think the reason we at Orange Capital Partners, we're working on the inference problem a little bit deeper. We want to educate ourselves a bit more because Musk actually spoke about this at the earnings call, and he mentioned that Tesla is really good at inference. And in our opinion, that's something worth thinking about to understand, okay, what does it take to be good at inference on the edge? What are the problems? And what are the solutions? And I think Attila's company and this podcast that he actually had at Software Engineering Daily, I'll put the link in the show notes, they're a good intro into this. So I think if you look at Attila's approach, I would call this a more of an engineering approach where you're trying to reduce the model. You see how many weights and biases do I actually need to perform at a certain level. Now, Ming Ding, he has a different approach, a little bit different. I would say there's really two interesting things that he was talking about. And one is he's working on video generation models for edge devices. In other words, if we have video generation, we are really looking at a lot more data, a lot more longer context windows. So that's probably another thing that basically. Okay, let's rephrase that. I think Ming Ding works on two fundamental problems. Number one, he is interested in video generation. The other is long context windows. And in both cases, the approach is very similar. And that is about compression and decompression and not losing too much information. So actually, one of the papers that he presented was an idea of a video transformer with upsampling. So imagine you have something like a video transformer. So you train an image generation model the same way you train GPT in a self-attention architecture, and you tokenize the image, let's say by pixel or by region of pixels. The way you tokenize something like that is a science in itself. And I actually asked the question, but it wasn't answered. But the question again is, okay, how can we, let's say we train the model, right? We train the model and we have billions of parameters, and we compress this model in a very useful way so we can generate videos. And we can use what Jensen Huang mentioned in one of his keynotes. We can use this tokenized video model actually as a compressor for video, right? We could send these tokens from A to B and then regenerate them, at B, and therefore save ourselves a lot of time in terms of transmission, transmission time and transmission compute and memory resources. So, think about the canonical example. If I tell you I just surfed on the beach in Half Moon Bay, these are very few words that if you are familiar with Half Moon Bay and the surf there, you have a pretty good sense for my experience there. And imagine the kind of compression that I was able to achieve with this model that we both have, your model and my model of surfing in Half Moon Bay. This same idea can be used in video generation. And Ming Ding is working on a problem similar to that, where they use transformer architecture and diffusion models to sort of upsample from the transformer into higher resolution videos. The way I understand this is, imagine you have a video transformer trained in a pre-trained manner with, again, billions of parameters. And that transformer is really good at generating me surfing in Half Moon Bay. It's really good at that. It can do that pretty well. Now, think about me working with an iPhone trying to generate a video where I'm surfing in Half Moon Bay. Like, you don't have access to the whole model. And one solution would be sort of the Atila Orhan solution that his company Argmax is pursuing, which is, okay, can I distill the weights and biases to the point where I can still reproduce crimp surfing in Half Moon Bay with pretty high fidelity? The other solution, or similar solution, maybe it's not an and, maybe it's an and or type situation, where we could sort of try to get a certain amount of video generation, let's say a low resolution video generated on my device, and then upsample from that. Use a diffusion type architecture to work with the given low resolution video into a more high resolution video. So that's one thing that Ming Ding is working on. The other thing is long horizon tasks. Now, long horizon tasks are challenging because they require a lot of inference time. Long horizon tasks are challenging because they require a lot of inference compute and memory resources. Imagine if you upload a whole movie and now you want to query the movie. So your prompt is the movie, 90 minutes of video. And you have to do inference on this. The challenge is, well, the challenge is really in compute and memory. It's not necessarily so much in the architecture itself, because you can do, this can be done, but it would take a lot of resources and be very expensive to do query on a movie like that. Now, again, maybe there's a use case for that in Hollywood and or the CIA and things like that, but for normal people, this is a challenge. And the solution to these types of problems, again, according to Ming Ding's presentation, lies in compression, sampling, decompression, diffusion. Those are sort of the big words that he's using. So he's betting on that. That's the direction that his company or his research is betting on. I was trying to find out what his PhD thesis was, and I couldn't find it, but I still think that, you know, his presentation, it was interesting. There's a couple of caveats here. I think one thing I noticed, just this is as a tangent, I checked his papers and the publications, and I realized that he has a lot of citations on his papers. And I would say that that's pretty laudable, but there's a bit of a suspicion in my head here that maybe there's some clickbait going on. Maybe the Chinese academics are sort of citing each other's papers here, or something like that is going on. Now, I don't want to be unfair to him or anything like that, but it just seemed a bit suspicious, because also a couple of papers, they all seemed the same thing with small modifications. Now, again, I didn't go into the technical weeds and details of the paper. I just want to put this out as a sort of, just as a note of caution in general in academics. When people talk about solutions to problems, when they have high citations, it's not always, not everything is always what it seems. Back to the presentation, I think what's interesting, again, as food for thought in general, if we look at the idea of video generation on edge devices, particularly iPhones and Android devices, some of these solutions like Ming Ding's approach, for example, or Atila Orhan's approaches are definitely feasible. Now, when it comes to robotics, self-driving cars or humanoid robots, the problems are slightly different. For example, a self-driving car has this potential to use a large language model for semantic mapping. And I believe that, and this can happen through a large language model or a video language model. In other words, you're taking images from the real world and you're transferring it into text and adding semantics to it. This is a school, be careful, there's kids around schools. This is a fire hydrant that is not working. Maybe you shouldn't park here. The water might splash out. I don't know, things like that. You add semantics the same way we humans add semantics. So that would be one line of thought. And the question, how can you compress a large language model onto a Tesla inference engine? And I think that's probably where Musk is going at with his idea of inference. I think what they're thinking probably, that's my guess, is to use the Tesla onboard chips as inference for the FSD fleet. So this would be one interesting line of thought. Nobody's ever talked about this concretely, but I just think that it's an interesting thought. This would be just use raw compute power for inference. Now, in terms of compression, I think again, Argmax's solutions to compression are valid and could be pursued also in the self-driving car space. Some of the Ming Ding solutions, like upsampling and stuff like that, that's also interesting, particularly in the visualization side of things. So when, let's say, Tesla visualizes the surroundings. I think overall, what I want to say is that the inference problem for edge devices is a very fertile research area. And I would encourage more work in this area on our side and in general also on the research side. Thank you.